Hi all, this is day 98 of my Gate CS prep journey. This is lecture 3 of data structure of asymptotic notation that I've started. So just now I'm done with big omega notation, and it's same as big O notation that we have seen. Only little difference you would see, but rest of the things are very much same. So you can see here the notation of it, and then theory is Tn is equal to big omega of g of n if and only if there exists constant c greater than 0 and n not greater than 0, such that for all n greater than or equal to n naught. So meaning is when we get value which is greater than n naught, then equation T of n is greater than or equal to C dot J of n. Always it satisfies this equation as soon as we get one value of n naught. You can see the graph also here. So after the n naught we get, right, so this Tn will always greater than C dot J of n, and before n naught you can see T of n is increasing, then G of n is decreasing or increasing, but after n naught it's like there is no change in it. So there, like from here we are starting with the examples. You can see we need to find if T of n is equal to big omega of G of n. So equation is T of n greater than or equal to C dot G of n for all n greater than or equal to n naught. Meaning of this is we need to find C and n naught such that value is greater than n naught, and it does not matter if value is greater than n naught or not. Then Tn should always greater than or equal to C dot Gn. So we have compared the equation with given value, which is T of n is n and G of n is 2n plus 6, and we have found the most dominating term. You can see here we on both sides n like same n is present but constant is multiplied. So on left side only n was there, but if nothing is there then that means n1 is present, so 1 dot n and 2 dot n is multiplied. So we need to take value of c here so that it should always less than the n, and we have taken accordingly, and then it was like satisfied the equation, which is c is 1 by 4 and n naught is 6. So taking this value depends on you need to build that logic, and you should understand like which value would satisfy the equation in this. So and then asymptotic comparison we need to do it like based on the most dominating term from both the side. So here it is the same on both the sides, so it would satisfy the equation which is T of n greater than or equal to C dot J of n, and which is also equal to omega of G of n. You can see we have seen same thing in big omega also, where it was like less than or equal to. Here T of n is greater than or equal to. Then second example is also same process we have to do, comparing the most dominating term. Here n square is there, so obviously like growth rate will be faster as we increase the value of n, and we'll get value of n square will be greater than or equal to this equation. So we have taken c equal to 1, and then n naught is 20, and it satisfies. So c is 1 and n naught is 20. I think we'll be doing a asymptotic comparison in next question here. So this question is again we need to find two constants c and n naught such that it satisfies this equation. Need to find two constants such that n is greater than n naught, and it does not matter. And T of n should always greater than or equal to C dot G of n. So this is n square on right side. Term will always grow faster as n increases, and some point n naught greater than like this left side term. So n naught exists where 2n plus 6 greater than n naught. So here c and n naught does not exist because 2n plus 6 cannot be greater than n square anytime. So c and n naught does not exist. So we are like before asymptotic comparison of previous question 2 is given here. Like you can see n square is greater than n, which is satisfying the equation, and which is equal to big omega of g of n also. Then asymptotic comparison of this question itself, which says t of n less than, like, it's not, t of n is not greater than or equal to j of n, it's less than or equal to g of n, so it does not satisfy the big omega also. So conclusion so far from this question is, from above example it can be concluded that t of n is big omega of g of n if and only if t of n is greater than or equal to c dot g of n asymptotically. So we need to remember big omega is greater than equal to, that's all for asymptotic comparison. For the function t of n and g of n, this we need to find, if satisfies, then need to find c and n naught. First do asymptotic comparison between t of n and g of n. If t of n is less than or equal to g of n, then t of n equal to 0. Big O g of n satisfied. We can see the examples here. We need to do asymptotic comparison. T of n is greater than c dot g of n for all n greater than or equal to n naught. Need to find two constants c and n naught such that value does not matter. So this is equal, so we can find the c and n naught. Both we can take here, they have taken 1 1, so it is satisfying the equation. This 50 n square 1 is 40, this then most dominating term asymptotically compared, and Tn is greater than the equation. C is taken 1 and n is 100, so it is satisfying. So C is 1 and n naught is 100 for this. Again here is 100, 1000 n plus 5000 n square plus 10. So after like comparing asymptotically, t of n is less than g of n, which does not satisfies the equation. So c and n naught does not exist for it. So basically you need to compare it. If it satisfies, then go ahead and find the value of constant c and n naught. But if it is not satisfying after doing asymptotic comparison between most dominating term from both the side, it does not, like, there is no point to go ahead and find the CM because it does not exist only. So same type of question we have seen in big O also, like there is one main equation given t of n and we need to find sub questions of it by finding most dominating term. So first most dominating term out of the t of n is n cube, and from a it is n cube. So it's satisfying the t of n greater than or equal to n cube true. You can see, just find the most dominating term, and from that you need to see if it is true or false. So it's very easy. N square n cube is greater than n square n cube. Here I want to show you something like for n, right? N is also, it's n cube would be greater than n. So constant, like here 10 raised to 8 is there. Any constant value, just take 1 and compare it. So n cube would be the greater than 1. And here also, but yeah, here n raised to 4 is there, not constant. So n cube is less than n raised to 4 and it's false. Where is constant? I think all n to the power are there. So there is observation. Big omega can be used to represent the growth rate by picking most dominant term. So we can write this t of n is equation, which is running time, also as time complexity. Everyone know, like running time interchangeably used as time complexity also. And we have taken most dominating term, in front of it we have placed big omega. So exact, we are not, n cube is not exact running time, so that's why we are using big omega notation here. For any input of length n greater than equal to n naught, algorithm will take at least c dot n cube time. So there is relationship between big O and big omega notation. we know that for big O, it's T of n less than or equal to G of n, and big omega we just seen T of n is greater than equal to G of n is greater than equal to T of n, so which is same. That's what they have mentioned here. Thank you guys for watching and subscribing to my channel.